Jnanam paramam dheyam. Knowledge is supreme.
But suppose you go to a helium atom or something, or a multi-particle system. Helium atom has 2 electrons. Just to make the system simple, let us take them to be non-interacting. It is not quite correct. But whether they are interacting or non-interacting, what has to be obeyed? If suppose I put the first electron in set of quantum numbers, let us put the first electron in the ground state, which is n equal to 1, L equal to 0 and S equal to half or Ms equal to plus half. Suppose you put the first electron. Can you put the second electron there whether it is interacting or non-interacting? This is also an experimental data. That is Pauli's exclusion principle. Okay. The second electron positioning should be such that both the electrons cannot have the same set of all the quantum numbers. So you can try to see even if the interactions are included, Pauli's exclusion principle cannot be violated, it has to be obeyed. So no 2 electrons can share the same set of quantum numbers. So what does that tell us? Whether the electron are interacting or non-interacting, Pauli's exclusion principle has to be obeyed. How do you incorporate Pauli's exclusion principle for 2 electrons which are non-interacting? Take the 2 electrons to be very far away in position, that the interaction is really feeble, that you treat it to be almost non-interacting. It is like a dilute system. What is a dilute system? Different atoms are so far away that you can pretend as if there is no interaction. Only when they start becoming concentrated, then you start seeing the 1 over r interactions between the repulsive interaction between the electrons also, right? So, but how do you write, if you are given 2 electrons far away in position, how do you write the wave function? How will you write the Hamiltonian? There will be a Hamiltonian for the first electron, there will be a Hamiltonian for the second electron. If there is no interaction between these two, you can write H1 plus H2 and you can write psi 1 wave function for the first electron, psi 2 wave function for the second electron. Those two are not talking to each other, which means the total wave function of the system given by H1 plus H2 is psi 1 into psi 2. But you have to also obey the Pauli's exclusion principle. How do you do that? This is where you need to know the formal classification, which I am sure you would have studied in your first year course. Why is it distinguishable in classical physics? Suppose I take 2 electrons, I can actually distinguish them in classical physics. What is the reason? They do not have a wave associated with it. It is a point particle in classical physics. Only when 2 of the electrons have a wave, they may start overlapping. Then you cannot say whether this overlap region, this part is this electron and the other part is the other electron. So the indistinguishable concept will start coming only in quantum physics. Classically, you can keep an eye on that electron. Okay, so it is distinguishable. Even though they are identical, classical physics, they will be distinguishable. But quantum, because you will give the wave form to those particles, the waves can overlap. In the overlapping region, it becomes fuzzy. You don't know what is your electron which you are keeping track. Okay, so it becomes indistinguishable. And there are also 2 categories of particles which are seen in the experiments. So in the context of Stern-Gerlach, there were 2 splittings which helped you to write S equal to half. But there are other particles which higher spins also. Okay, so there are 2 categories. One is bosons, where the spin This is an internal space. This is not your orbital angular momentum. This is a new quantum number. Everyone had heard about this great news about God particle, right? The God particle belongs to the s equal to 0 at least. There are signatures that it's been, we have got God particle and then s equal to 0 is also more or less zeroed in, okay. So they are bosons. Bosons have integer spin. What about photon? Photon, how many possible polarizations are there? Why 2? What about the longitudinal one? Photons are massless, so you have only the transverse polarization. There are 2 of them. But if you make it massive, then you can also have the longitudinal polarization. So there will be 3 for a massive object, and that 3, how will you account? S equal to, if there are 3 states, S has to be 1, and so on. So every object which we see in the experiments in particle scenario either will have an integer spin or a half integer spin. So how do they see the spin? Is that they go to the rest frame where the orbital angular momentum is 0. They still see there are 3 states. If they see 3 states, then they will say this particle should belong to the s equal to 1 in the rest frame, because the orbital angular momentum L is 0. In spite of that, they see 3 states, then they will say that the object is a boson with s equal to 1. What are the other bosons which we see in the experiments in particle physics? Is that we have weak interaction, weak nuclear force interactions, where we see the vector bosons, the W plus, W minus Z. I am sure you would have just read as data. They have 3 states. So they are like the spin 1 boson. That is why it is called vector boson. Vector means that there are 3 components is what we are familiar, right? Fermions also, one of the fermions which you have seen in the hydrogen atom and Stern-Gerlach anomalous is s equal to half. But you can also have other kind of higher half-odd integral like spin 3 by 2. So if you have spin half-odd integral, you call them to be fermions. Okay. So these are 2 classes. There is no way a boson can become a fermion. Bosons have a different property. What is the property? It doesn't need to obey Pauli's exclusion principle. That's why you had this famous Bose-Einstein condensate. You can put any number of bosons in the ground state. Whereas if I give you any number of electrons, you can't put everything in the ground state. Pauli's exclusion principle prevents it, and you have to stack it and you will get a Fermi energy. Right? So this is the formal classification. If you have a system of identical particles in quantum physics, there can be integral spin particles which is bosons or half-odd integral spin particles which is fermions. Electron is a fermion and bosons are all the vector particles, including the photon. You can call it as an integral spin. Okay. How do we write this wave function? So I have already said that identical particles are distinguishable because we can keep track of the trajectory of the 2 particles by putting some color on it or marking on it. But in quantum physics, they will have wave functions and they start overlapping. So they become indistinguishable. And you can try to classify them as integral spin or half-odd integral spins. And the integral spins are called bosons, half-odd integral spins are fermions. Yeah, so there is this, one is when we have composite objects, we have a particle which is it's called delta plus particle, okay. There are particles which are made of 3 quarks. Proton is also made of 3 quarks, but that belongs to the spin half. But there are particles where you can combine 3 quarks which can give you spin 3 by 2, which are like the delta plus particle, omega particle and so on. If suppose you have 5 electrons and you make a bound state of 5 electrons, it can have the total spin of that bound state, maximum value could be a 5 by 2. Some subset of it can behave like a spin 5 by 2. There will be some subset will behave like a spin 3 by 2. Some subset will behave like a spin half. So these things we will get into it at some point. Okay. Yeah. But the upper bound is that if you have a composite of 3 quarks which each one is spin half, I am trying to say that you can have a spin 3 by 2 object which is a composite. You can have a spin half object which is a composite and so on. Proton belongs to spin half composite, whereas your delta plus and omega particles belong to the spin 3 by 2. But you don't find in the lab a spin 5 by 2. In the composite particle physics, they are all called hadrons. The zoo of hadrons don't have a spin 5 by 2. So that's why we tried to say that at most these composites should be made of only 3 spin half particles. So far I have tried to take you on the bosons and the fermions, and let's just take a simplest situation. 2 particle system in 1 dimensional potential well, and write the wave function should be a function of position of the first electron, position of the second electron. This x1 and x2 is still in 1 dimension, but the subscript 1 for the first electron, subscript 2 for the second electron. This is the kinetic energy for the first electron, this is the kinetic energy for the second electron, and it has to be satisfying your time independent Schrodinger. So what is the solution? So you can write the solution to this equation as a product of solutions to each electron if they are non-interacting. Why is it non-interacting? I have not put a V which is coupling x1 and x2. That's why it's non-interacting. So for such a non-interacting electrons, so particle in a box will have only one quantum number, which is n1 and for the particle 1 and n2 for the particle 2. And they are identical. What will you do? You can write the composite wave function to be product of particle 1 in quantum state n1 and particle 2 in quantum state n2. Or you could also write particle 1 in quantum state n2 because they are identical. You can't distinguish. What else can you possible? Both are equally possible. A linear superposition is also possible. Right? You can take a linear superposition of them, that is also possible. But you should take a linear superposition in such a way that when I put both the electrons in the same quantum, suppose I put both the electrons in the same ground state or same first excited state, what is the meaning of that? N1 has to be equal to N2. But Pauli's exclusion principle does not allow. So what linear combination you can take? You have to take a linear combination so that that composite, when both N1 equal to N2, it has to be 0. But do we see that here? If you put N1 equal to N2, the solution exists. If you put N1 equal to N2, the solution also exists. So this are not valid by Pauli's exclusion principle. What is valid is, you have to take a linear combination. When I put N1 equal to N2, the wave function has to vanish. That's it. There is no such solution possible. Only trivial solution. So probability density, if you try to work for this case, it is not the same, and you want the Pauli's exclusion principle to be satisfied. That is, the wave function has to be 0 when you put N1 equal to N and N2 equal to N. So how will you achieve both of them? You can write plus or minus. Which one is right? It's a minus sign which is right. For the electrons. Suppose I replace the electron by a boson, we'll put a plus sign. Because it should be non-zero. You can't have a minus sign. Clear? And this will also take care that the probability density, the plus sign, plus 1 and minus 1 is very important. So you can see that for a 2-particle system, even for non-interacting, the wave function should be either, the plus sign can be also interpreted as symmetric under exchange of particle 1 and particle 2. Minus sign can be interchanged as if you exchange particle 1 and particle 2, you get a negative sign. These are like your odd functions and even functions which you are studying, where you took x2 minus x. Here I am saying make the first particle and the second particle exchange. Under exchange, the wave function is antisymmetric for electrons and symmetric for bosons. So this will extrapolate if you had 3 particles. You have to make it totally antisymmetric, and for bosons you can make it to be totally symmetric. Okay. So I am just giving you a flavor that you can try to write the wave function for a 2 electron system as an odd function with the minus sign. This should become the minus sign. Similarly, the even functions is allowed for bosons. What do you do for the hydrogen atom problem? I did this for a particle in a box. You formally say that the first electron is in a state alpha. Alpha is a compact notation which tells you it has this alpha is N alpha is the principal quantum number, L alpha is the azimuthal quantum number, ML alpha, MS alpha. The S can be suppressed because for electrons you know S is half. You don't need to explicitly put the half. Okay, similarly put beta for the other state. Write down a total antisymmetric where alpha, the longhand notation for alpha is the 4 quantum numbers. Similarly beta, it is again the 4 quantum numbers, and those two should be different. At least one of them should be different. Clear? And this is what I was trying to say. You can write the position space wave function which depends on only the orbital quantum number and magnetic quantum number, but you can put a product which is a new space which doesn't talk to them, put that wave function with an m, the magnetic quantum number. Okay. So this is a formal way in which you can write your wave function as a product of the position space wave function times a spin state. A spin state does not have any projection on the position basis. It's an internal space. So this one is independent of R1 and it's introduced by hand to match with experiments in non-relativistic. So if you take 0 velocity, you can ignore that this wave function is almost like the S wave, and you can concentrate on the spin part of the, take n equal to 1 or even for any n L to be 0 situation, then you can concentrate on this part of the wave. This is the beautiful concept that these two states are like the 2 bits in your computer's binary operation which we do. All the computations which are done involves only playing around with 0 and 1, right? 0 and 1 binary, then bytes is how many bits? 8 of them. Each one is called as a bit which is 0 and 1, and you can have a byte which is 8 of such bits. What does quantum mechanics tells us? These are also 2 states. So just to keep track, it is quantum mechanics, we call them as qubits, okay? And they are also 2 states, but there is much more. In the 0 and 1, you can keep adding 0 and 1. But in the context of qubits, you can take superposition. You can start taking superposition of various possible qubits. So this is, this is supposed to increase your speed, supposed to enhance what all you want to do in a much more efficient way, is what is the, is what we all feel, okay. So just to give you that qubits are 2 states of the spin half electrons. powerful than classical bits, because there you just play around with only 0 and 1, but here you have superposition of qubits. Algorithms have already been written in the literature. I'm sure some of you would have known at least. So they are called quantum algorithms. They are definitely efficient, especially the factorization problem can be solved in polynomial time, Shor's algorithm. Okay. So these have been achievable using qubits. And lot of work, there are a lot of problems, gravitational wave detection. Why couldn't we detect it? Took so long. Why? There's so much of this background noise and it's such a feeble thing, right? So similarly, this quantum computer construction, even though theory can be a lot of incoherence, so many things have to be taken care of, and that's itself a challenge. People are working on it. They have tried to make a couple of qubits together, couple of qubits together. Still, it has not reached a level that we have a quantum computer, but people are at it. Because theory wise, we do see that there will be a lot of efficiency in the computation, can do things faster. Still, it's at the research level. Okay. So, I thought I should give you some motivation before we get into doing this hardcore calculations in Stern-Gerlach experiment, that why it is spin half and why a lot of excitements are going on. Okay. So, I will stop here.